the traditional biennial workshop we planned as usually at ISRANALYTICA in Tel Aviv in Israel, but because of pandemic, this year the transformation was done to webinar, as we have not another way to hear what is new in the development of the projects on the topic of conformity assessment, on metrology and chemistry more wider than conformity assessment, and chemometrics. So I'm happy and thankful to you, Zoltan, for the possibility to use your facilities of Zoom. And I ask you to start the introduction as it was planned according to the agenda. And so all the speakers as it was planned in the agenda.
Thank you, Ilya. So I would attempt to launch my presentation. So good morning or good afternoon or good evening, everyone. It is my great pleasure to open this workshop on behalf of the sponsoring organizations of IUPAC and CITAC. I would speak as the opening in my opening notes only on behalf of IUPAC because we have the pleasure to having on this call Bernd Gu, who is the chair of CITAC, who would be saying a few words on behalf of CITAC. So I would like to open the seminar on metrology, quality and chemometrics, correlation of test results, mass balance influence on conformity assessment. So a few words about IUPAC. IUPAC was formed after the great calamities of the first war in Europe, recognizing that multilateral development of language and standards and agreements on chemistry are key to further success of the discipline and further development of the world. So IUPAC was formed in 1919 as an association of chemical societies, as a non-governmental, international non-governmental organization. And IUPAC was kind of the template for this multilateral international science organizations for a century to come. IUPAC is currently a global organization that provides objective scientific expertise and develops essential tools for application and communication of chemical knowledge for the benefit of humankind, accomplishes its mission by fostering sustainable development, providing language for chemistry, and advocating free exchange flow and exchange of scientific information. And as a result of these activities, IUPAC effectively contributes to the worldwide understanding and application of chemical sciences to the betterment of humanity. It's a truly international organization with 57 nations participating. The major activities of IUPAC relates to development of language for chemistry, nomenclatures, symbols and terminology, standardization of chemistry for data presentation on chemical methods, critical evaluation of chemical data, think here about atomic weights, your periodic table, thermodynamic and kinetic data sets published by IUPAC. IUPAC is also active in computational issues, in data exchange standards, and it's a major sponsor of scientific conferences and a contributor to betterment of chemical education standards. Our outreach or publication forums are the Pure and Applied Chemistry, which is a peer-reviewed analytical journal where IUPAC recommendations and reports are published. Chemistry International, which you might be receiving in your email boxes these days, which is a news magazine, and the IUPAC Color Book series, which you might be familiar with, which covers all major fields of chemistry, providing nomenclature guidance. IUPAC is working in a divisional structure covering major fields of chemical sciences. Metrology and metrology-related activities are coordinated from the Analytical Chemistry Division, which I have the pleasure in this current biennium to lead. And a quick review of our division. Analytical Chemistry Division of IUPAC provides the highest level of expertise in line of IUPAC's mission related to analytical chemistry by publishing technical reports, recommendations on terminology, evaluating chemical data, contributing to standard development, and providing scientific advice, unbiased scientific advice to relevant international organizations. Again, reminding you that IUPAC is an NGO, is a non-governmental organization. So in this structured world, unbiased scientific data to governments or intergovernmental organization is a rare commodity. IUPAC Analytical Chemistry Division provides the language for analytical chemistry. A shameless plug here for our latest edition of the Orange Book, which is the compendium for terminology in analytical chemistry. IUPAC Analytical Chemistry is fostering and promoting the development of analytical discipline itself by organizing meetings and symposia, hence this event here today, contributed to issues related to chemical education, and award outstanding contribution towards the goals of the Analytical Chemistry Division. Another plug here that our recently established Emerging Innovator and IUPAC Analytical Chemistry Medal Awards nomination period is coming to a close by the end of this month. So I would invite you to nominate your worthy colleagues to this for this prestigious award. You can find details on our website. How to get involved with IUPAC? IUPAC is working through a project system. So the simplest way to get involved is to propose a project idea related to nomenclature, data validation, standard development, education, or any other subject related to chemical development, which requires worldwide consensus of chemists, so can benefit from the wide-reaching organizational structure of the union. So again, we are here today to celebrate this project through this symposium. So without further ado, I would like to hand back the podium to Dr. Kuselman, who is leading this project. So if you have any questions, comments, please reach me privately, and I would like to share with you more information about the union. Thank you. Ilya, the floor is yours.
Zoltan, if you have questions, I propose strictly according to the agenda to continue because we have a special lecture on the project by Dr. Francesca Pinecchi, and also my lecture is close, like introduction to this project. So we will talk about that. But now, because we have only 2 hours for this webinar, I propose to organize it strictly as it is written in the agenda. So it is the time of the introduction by CITAC Chair, Bernd Gu.
Yes, can you hear me? I have my microphone open now. Zoltan, can you put me online?
Yes, we have you, Bernd.
Okay, good. So I don't want to speak too long to keep the time scale all right. My name is Bernd Gu, and as I already said, I'm the current chair of CITAC, and it is my pleasure to welcome you all here for this IUPAC CITAC workshop on behalf of CITAC. CITAC, the Corporation for International Traceability in Analytical Chemistry, was founded at the beginning of the 1990s, shortly before the formation of the CCQM, the Consultative Committee for Chemistry and Biology, at the MITA Convention. And it was a time when the issue of traceability in chemistry became internationally very apparent and obvious. So CITAC aims at the worldwide dissemination of information about traceability in chemistry, and this workshop is actually a very good example for the kind of work that we usually do, and we all are happy to have you here and listening to this workshop, and we want to continue these activities in the future as well. Of course, we are living in a strange time and things get more complicated than they used to be in the past. And the dissemination of knowledge about metrology, also in the form of workshops, is a key activity of CITAC. And we had to change and adapt to provide these services also in pandemic conditions like other institutions too. So we all have to meet electronically now. And this is indeed the second CITAC workshop that is purely based on a video platform. And I have to say that not everything is negative about this virtual approach. Besides saving travel expenses, as you all know, we also appreciate the wider audience that we can reach in this way. And this actually tells us a story, and we will certainly integrate virtual technologies also in future meetings of this kind, even when we are back to normal life. And I think I'm speaking for the executive committee and whole of CITAC on this issue. The good news of today is that we are getting closer to this normal life every day now, and it is a special pleasure for me to look at Israel. That would have been the host of this event in normal life. Here, with a vaccination rate of some 30% in Israel, we are already closer to this normal life again than anywhere else in the world. So congratulations, Ilya, to you and the perfect organization in your country. So it is a good thing to have virtual meetings or video conferences available at this time, but I also have to say that I look forward to seeing you all in real life again, preferably in Israel, not too far in the future. So I wish you all an inspiring and exciting workshop, and I'm pretty sure we can achieve that also in these days. All the best to all of you, and stay healthy.
So, thanks, Ben, for nice words. I personally, 1 hour ago, has received the second dose of the vaccine. So more or less, I'm defending against the pandemic now, I hope. But the next introduction, we are waiting from Michela, Sega, past chair of CITAC.
Thank you to all of you. So I will try to share my screen, and okay. So good morning, afternoon, or evening, depending on where you live, to everyone. I would like to thank the organizers, and in particular Ilya, the chair of this webinar, for giving me the possibility to be active part of this event. As CITAC past chair and as a stakeholder of the current IUPAC project on the influence of a mass balance constraint on uncertainty of test results in non-conformity assessment, it is my pleasure to welcome you all once again to this webinar and to act as its moderator. The participation in joint projects and the organization of joint events by IUPAC and CITAC are two important outcomes of the fruitful cooperation between the two organizations. Today's event is a great example of such cooperation at an international and worldwide level. If you have a look at the agenda of today's event, you can see that all the 5 continents are represented. And so this is once again a good example, good proof of the worldwide impact that such cooperation has. We are now going to start with the 4 lectures that will be given by excellent scientists and also very good friends. I would like to remind the speakers to keep the presentations within 20 minutes in order to give some minutes left for questions. I would suggest if someone wants to ask a question to the speakers to write it down in the chat in order to optimize the flow. So let's start with the first speaker, Dr. Ilya Kuselman himself, the webinar chair, who is an independent consultant on metrology from Israel. He will give us a lecture on the IUPAC CITAC guide, evaluation of risks of false decision in conformity assessment of a multi-component material or object due to the measurement uncertainty and correlation of test results. Please, Ilya. I will
Thank you.
connect myself.
The recently published IUPAC CITAC guide on evaluation of risk of false decision in conformity assessment was developed according to the IUPAC project since 2016, the work of 5 years already, by the task group consisted of Dr. Francesca Penecchi, INRIM, National Metrology Institute of Italy, Professor Ricardo de Silva, University of Lisbon, Portugal, Emeritus Professor David Brim-Hibbert, University of New South Wales, Australia, and me. The work was supported by CITAC. I will talk about main issues of the guide, starting from a short introduction to conformity assessment and decision rules in this field, and risk of false decision due to measurement uncertainty. Then we will discuss the Bayesian approach to risk evaluation, modeling total risk for independent properties of a material, concentrations or contents of components, and necessity to take into account, in some cases, correlation between them, examples and conclusions. By ISO 17000 standard, conformity assessment is demonstration the specified requirements relating to product or system are fulfilled.
Ilya, sorry to interrupt you, but you didn't share the screen. Could you please do it? Sorry.
Yes. Okay. Okay. Now it is visible?
Great, yes.
Okay. Okay. Comparing the test result measured value with the limits of the tolerance specification interval of the material, one decides whether the tested concentration conforms or not. Tolerance limits refer to true concentration values, whereas the interval of permissible measured values of a component concentration is the acceptance interval taking into account measurement uncertainty. This diagram shows the decisions on conformity of a component concentration in material to requirements stated using tolerance interval for the concentration. when true value, concentration value is in the tolerance interval, the material is good, and if one of the limits of the tolerance interval is violated, the material is bad. The true value is known to God only, and the man uses a measured value, which is compared with the limits of acceptance interval. When decision pass is made to a good material, it is correct decision, and the same decision for a bad material is false, incorrect decision, which is the particular consumer's risk. Particular is because we are talking about a particular component. The decision fail for a good material is also a false decision, but it is already particular producer's risk. The decision fail for a bad material is the correct decision. GCGM 106 guide provides a methodology of conformity assessment by comparison of a test result with the tolerance limit, taking into account measurement uncertainty and corresponding risk based on the Bayesian approach for univariate conformity assessment. Knowledge about an item property, concentration of a component in the material, the measurand, can be treated as a random variable and expressed in terms of probability density function, PDF. Such a PDF combines by the Bayes theorem prior knowledge of the measurand and new information acquired during the measurement. In this formula, the posterior PDF is shown as normalized product of prior PDF and likelihood function describing the measurement uncertainty. Particular specific producer risk is the probability of the false decision that a specific item, sample, or batch should be rejected. It is probability of rejecting the null hypothesis. The particular component concentration is in its tolerance interval, when in fact the null hypothesis is true. The step 1 error according to ISO standard 3534. There are lower tolerance limit of the tolerance interval on the figure and lower acceptance limit of the acceptance interval. The distance between them is guard band for a consumer in mechanical and material fields, or gray zone in microbiology and some other fields caused by measurement uncertainty. The integral from the lower tolerance limit to infinity is the risk. Particular specific producer's risk. Particular specific consumer's risk is the probability of the false decision that a specific item conforms. It is the probability of failure to reject the null hypothesis that a particular component concentration is in its tolerance interval, when in fact the null hypothesis is not true. This is type 2 error. Particular global producer's risk is the probability that a conforming property value of a particular component will be assessed as non-conforming based on a statistical analysis of earlier performed test results. The measured value is outside acceptance interval, but the true value is within tolerance interval. This risk corresponds to the producer's risk of the incorrect assessment of a particular component concentration in an item randomly drawn from a statistical population of such items. It characterizes the material production object globally. Particular global consumer's risk is the probability that a non-conforming property value of a particular component will be assessed as conforming based on a statistical analysis of earlier performed test results. the measured value is within acceptance interval, but the true value is outside tolerance interval. Note that a multi-component material or object is not simply a mixture of any components or their sum. When particular conformity assessment risks are acceptable, the total probability of a false decision, total consumer's risk or producer's risk on the conformity of the material as a whole might still be significant. The term total risk is derived from the law of total probability, a fundamental rule which expresses the total probability of an outcome realized via several distinct events. Bayes' theorem for a multivariate case is in general the same, but the prior, likelihood, and posterior are multivariate. Here, eta true values and eta m measured values are shown in bold as they are also multivariate. Therefore, total specific producer risk is the probability that the true concentration values of all components in a specific rejected item are conforming when at least one of the measured values is outside its multivariate acceptance interval. Tolerance interval here is a multivariate region, and the integral is multiple also. Total specific consumer's risk is the probability that a specific accepted item doesn't conform as a whole when the true concentration value at least one of at least one component is outside tolerance interval. In other words, the total specific consumer risk is the probability of a false decision that an item is conforming based on the measured values not violating their acceptance limits. Total global producer's risk is the probability that a material with conforming concentration true values of all the components will be rejected based on a statistical analysis of early performed measured values. For simplicity, for the case of two components under control, the total risk can be expressed based on law of total probability as the shown here combination of the particular risk and their interaction. Here, B with hat means the event when all true values are in tolerance interval, while C with hat means the event when one of two or both measured values are out of acceptance interval. C1 and C2 with hats are events when measured values are out of the corresponding acceptance interval of the first or the second component respectively. Total global consumer risk is the probability that the material with non-conforming concentration true values of one or more components will be accepted based on a statistical analysis of early performed measured values. Similar expressions for more than two components under control can be formulated using the same multivariate modeling for independent and correlated events. There is the map of risk of false decision and conformity assessment, producers and consumers risk, relevant to each particular component I of material under testing, formulated as specific and global particular risk for each N components of the material. This is what described in GCGM 100 guide. The second part of the map, shown in the red ellipse, is related to producers and consumers risk relevant to the material as a whole, including total specific and total global risks. This is what described in the IUPAC CITAC guide about which we are talking today. In general, there are 4 N+1 kinds of risk of false decisions. Evaluation of total risk based on the law of total probability is applicable in absence of correlation of true values as well measured values of concentration or contents of components of a material. When and why correlation may arise? Let's start from metrologically and human-related correlation possible in multi-component chemical analysis. Swiss cheese model of a quality assurance system against such a correlation in analytical laboratory is shown in this slide. In practice, any quality assurance system is never hermetic. Every layer of the quality system, as layer of the cheese, has holes. And when the holes coincide in the way of an analysis, test results can be correlated. If a statistically significant correlation between measured values of concentrations or contents of components of the same sample is detected, analysis cannot be continued without a thorough chemical analytical inspection of the reason for the correlation in the laboratory. However, test results of chemical compositions of a batch, lot, or object are inevitably correlated when their actual true values are correlated. Correlation of contents of sample components can be caused by natural physicochemical properties of substances, such as stoichiometry, and by technological reasons in the material production. When components of a substance or material are subject to mass balance constraints, sum of the components contents is 100%. Test results of the material are called compositional data. These data are intrinsically correlated because of the constraint. The relevant correlation was termed as spurious. More on this topic you will hear in the next lecture by Dr. Francesca Pinecchi. There are two examples in the guide of the cases of independent variables, concentrations of the components, and the next two are on correlated variables. The first example is on conformity assessment of the denatured alcohols for customs control, where a prior normal distribution and normal likelihood function were used for modeling. The second example is on conformity assessment of concentration of total suspended particulate matter in ambient air, where a prior log normal distribution and the normal likelihood were applied. The third is on conformity assessment of a medication where technological correlation was detected, normal prior and likelihood were used. The first example is on conformity assessment of chemical composition of a platinum-rhodium alloy with technological and spurious correlations, normal prior and likelihood approximations. In conclusion, there are cases of independent concentrations or contents of material components. At the same time, three kinds of correlations are possible: metrologically human-related, stoichiometric, natural and technological, and spurious correlation. The multivariate biasing approach to conformity assessment can be safely used in both the cases of independent and correlated test results measured values. And modeling experimental data consists of assigning PDFs to the involved variables according to the state of knowledge on them. That's all. Thank you for attention.
Thank you to you, Ilya, for your nice presentation. Are there any questions? I don't see anything typed. I would like to ask you on which kind of priori information did you base your consideration for to modelize the a priori knowledge of in the examples of the guide?
In our examples, we used the data sets accumulated at factory. If we are talking about for example, medication, or in the case of particulate medicine ambient air, it was the data set of the National Physical Laboratory of Israel. In any case, the preliminary information is a kind of data set which is accumulated in a laboratory. We are talking about prior distribution as a distribution of true values, but again, true values are unknown for us. So the approximation is the data set enough large. In many cases, it is more than 70, 80 batch or 70, 80 lots of product, and to have a good model which could be used as preliminary knowledge about the process and the measurement influence on the distribution.
Thank you so much, Ilya. Are there other questions or comments? I see there is a question here. May I ask the colleague to ask directly to Ilya the question, please? Well, I'm trying to read it. Is the UOM the only mean to decide the pass and fail of products, or are there any other criteria?
What is UOM? Uncertainty of measurement.
Yeah.
Uncertainty of measurement uncertainty we are talking about is influencing probabilities of false decision about quality or conformity of material. Yes, there are two possibilities. We can decide that the batch or lot is good or bad. And in these decisions, we may do an error or may do a false decision because of measurement uncertainties. So the topic is to understand how measurement uncertainties influence on probability of false decision on the material, on its quality, its conformity to requirements of a standard or technical conditions or legislation.
Thanks, Ilya. There is another question. What can be the origin of metrological correlation?
I talked about that and in the conclusions. First, if we are talking really about correlation of test results of different components, not the correlations of two technicians which are working hand by hand in the same laboratory, but about the correlation caused between the measurement results, measured values of different components in the same sample. There are stoichiometry. If we are talking about analysis of a compound, the technological reasons, when, for example, for medication, the quantity of every active component is normalized for a drug. In each tablet, it should be the specific quantity of one active pharmaceutically active component, and second and the third, and also even about the components which are not pharmaceutically active. So these limitations will lead inevitably to the correlation of measured values. And also spurious correlation, about which we will hear more in the next lecture by Dr. Francesca Pennecchi.
Okay, thanks. There's another question. I would say the last one. So in case of qualitative results, how can I apply the decision rule in passing or failing of the product?
In qualitative analysis?
Yes.
In case of qualitative results, I cannot answer today because all this project was for quantitative results. Of course, the case of qualitative results has his nuances which should be taken into account. All about what we are talking today is related to quantitative contents of components or concentrations and respectively quantitative measured values. The topic of qualitative results was taken into account in these projects.
Thank you. Yeah, so good suggestions for an additional work. Thanks. Thanks, Ilya. Thanks to everyone for the comments. And I would like now to pass to the next speaker. The next speaker is Francesca Pennecchi, from Dr. Francesca Pennecchi from INRIM, the National Metrology Institute of Italy. And she will give us a talk on the topic influence of a mass balance constraint on risks in conformity assessment of substances and materials. Francesca, the floor is yours.
Yes, thank you, Michela, for the introduction. I'm going to share my screen. Okay. Hello, everybody. Today I'm going to talk about this IUPAC CITAC project. I will not repeat again the title because it's very long. The project is dealing with the two important topics, that of the mass balance constraint and that of compositional data. The aim of the project is to adapt the Bayesian framework of the conformity assessment that Ilya has just explained to us to the compositional data. I will show you a couple of case studies and then I will come to the conclusions. The project started in July 19 under the chairmanship of Ilya and with the collaboration of Brian Hibbert, who will be giving his presentation after mine, Aglaia Di Rocco from the University of Torino, Italy, and myself. There are several cases in analytical chemistry, all we know, I think, where the components of a substance or material are linked to a mass balance constraint. That is, the sum of their mass fraction or molar fractions, for example, has to be equal to 100% or 1. In this case, the test results of such components' contents are named compositional data. These data are inherently correlated because of the mass balance constraint. The induced correlations are called spurious, as already anticipated by Ilya. Spurious correlation is a kind of mathematical property of the data that is not related to any physico-chemical interdependence between the components, but that can actually have an influence both on the measurement uncertainty in the test results and on the risks of erroneous decisions in their conformity assessment. Therefore, this spurious correlation needs to be studied and modeled appropriately together with the requirements imposed by the mass balance constraint. The topic can have an important impact on the testing of geological and environmental objects, products of metallurgical and food industry, and so on. Today, I'm going to present the main output obtained so far within the project, encouraging you to stay tuned on the future developments that will be published on the project website. The raw vector C is defined as an n-part composition when all its components are strictly positive real numbers and they carry only relative information. The fact that the compositional information has a purely relative nature is also clear by the corresponding measurement units like weight or volume percent, ppm, ppb, molar proportion, and the like. The sample space of compositional data is called the simplex, defined as the set of all vectors whose positive components sum up to a certain constant, k, usually 1 or 100, which means respectively that the measurements have been in parts per unit or in percent. Compositional data analysis theory has been developed since the 80s, starting from its very pioneer, the Scottish statistician John Atkinson. Since then, several examples of application have been developed in geochemistry, astrophysics, material science, and many others. There are specific conditions that should be fulfilled when dealing with compositional data. Without entering the mathematical details here, the first one, the scaling variance, derives from the fact that the only information carried by a composition is provided by the ratios between its components. Indeed, if we multiply all of the components by any positive constant, for example, by a change of units, we are actually retaining the same amount of information as it was in the original composition. Hence, it is natural to select a representative of this class of equivalence, and this is usually formalized by the closure operation, in which the single components of the vector are rescaled in such a way to sum up to a constant k. Compositional data can be plotted in a multidimensional simplex. In the figure here, the orthogonal coordinates in the star-band Euclidean space are shown on the left side of the figure, whereas the corresponding simplex is on the right side. Each vertex of the simplex corresponds to 100% of the relevant component Ci. For any dimension d, you can see that when moving from the left to the right, the mass balance constraint reduces the number of dimensions by 1, since each of the components can always be exactly recovered by 100% minus the sum of the others. As a consequence, ordinary covariance matrices become singular, for example. So to overcome these and other problems, one can resort to suitable variable transformation based on the logarithm of the ratio of the components. However, applying this approach to the Bayesian framework for conformity assessment would arise some difficulties. The modifications according to the log ratio transformations that should be applied both to the multivariate tolerance regions and to the involved PDF, probability density function, would complicate the framework a lot. Hence, the aim of the IUPAC CITAC project is to extend the Bayesian framework developed in the guide described by Ilya to the data that are restrained to a mass balance constraint. These data are a particular subset of the correlated multi-component materials or objects we have been talking so far. Again, the knowledge about the composition can be modeled by a random multivariate posterior PDF, which is a combination of a prior knowledge about the measurements, modeled by a prior PDF, and the new information acquired during the measurements. The latter is modeled by a multivariate likelihood that takes into account measurement uncertainty and possible covariance terms between the measured value. In the case of a mass balance, of course, also the spurious correlation should be taken into account among other possible sources of correlation, and the mass balance constraint has to be satisfied as well. The first step is to model the available information on the involved quantities by means of appropriate PDF. In general, a according to the principle of maximum entropy, a multivariate normal distribution is used as a prior PDF when the expectation, the mean value mu, and the covariance matrix P constitute the only available information about the vector quantity. Anyway, if a further information is available, that is, the fact that the C, the true values C are positive, hence the maximum entropy distribution is a truncated multivariate normal distribution with the same parameters mu and B. Such distribution, the multivariate truncated, assures that each component content is enclosed in a meaningful physical range, for example, between 0 and 100%. Accordingly, also the likelihood function for the measurement results can be modeled as a truncated multivariate normal distribution. Now, the parameters are the vector C of the actual true values and the covariance matrix U of the measurement results. In the plots here, you can see just an example of a univariate and a bivariate truncated normal distribution. Let us have a look at a couple of examples now. The former version of this example is reported in the IUPAC CITAC guide presented by Ilya, with the aim of modeling and calculating the total risks in the conformity assessment of a platinum-rhodium alloy, seen as a multi-component material with a complex nature of correlation. The evaluation of these risks was important for understanding the quality of such alloys, which are widely used in thermocouples for temperature measurements, oxidation catalysts, electronics, glass industry, and so on. In the present project, the same example is reconsidered, but focusing on just 3 of the 4 original components, those that were perfectly compositional, namely platinum, rhodium, and impurities. According to a relevant standard, these are the lower and the upper specification or tolerance limits. We relied on the test results from a total of 100 batches of such alloy, produced at the same plant during 2 years. The population mean and the standard deviations are here reported, together with the Pearson correlation coefficients between the 3 components and the typical measurement uncertainty. Note that the content of platinum has a negative correlation with rhodium and impurities, since platinum is determined exactly as 100% minus the mass fraction of rhodium and impurities. And as well, the uncertainty for platinum is calculated according to the same mass balance model. In order to model the multivariate prior PDF for the actual C values, we considered 3 possibilities. Model 1. In Model 1, we draw random values from a multivariate truncated normal PDF, as said before, with the mean mu and covariance matrix B recovered by the prior knowledge on the batches populations. Then we close the data, hence modeling their composition and nature. In general, this approach is suitable for materials whose composition is tested completely, and the test results should meet the mass balance. In Model 2, instead, we assign again a multivariate truncated normal, but just to the second and the third component, using the correlation between the 2. Whereas the content of the first component, the platinum, is deterministically obtained as 100 minus the others, hence again assuring the mass balance constraint. This model can be applied for pure substances or materials in which the main component content is not directly measured, but is calculated as 100% minus the other contents. Then we investigated also Model 3, where one content at a time is modeled with a univariate truncated normal, starting from rhodium, then impurities, and finally platinum, again recovered as 100 minus the others. This modeling approach, we call it sequential, is more complicated since the sequence of C2 and C3 in this case could be exchanged, and this may lead to different results. For the 3 models, we drew 10 millions of Monte Carlo random values from which we calculated the correlation coefficients and the conformance probability. Comparing the results with the original experimental ones, the blue ones, we can see that the correlation coefficients obtained by models 1 and 2 are essentially equal to the experimental ones within the precision of the Monte Carlo simulation. Therefore, we can say that the 2 models seem to correctly reflect the a priori knowledge. Larger differences are encountered in results by Model 3 instead. And this is because the correlation metrics generated by Model 3 can reveal only the correlation that arise from the truncation effect and the mass balance constraint. It is not able, in fact, to accommodate other sources of correlation. In the present example, the sum of rhodium and impurities contents is well far away from 100%. And the correlation between the two, due to the truncation effect, is practically negligible, despite the fact that the experimental correlation originally was 228. As a general comment, this model cannot be implemented adequately when natural or technological correlation are significant. On the other hand, we have to say that it could be helpful for disentangling the spurious part from the total amount of correlation. Then we have to model the likelihood function. The modeling of the likelihood function follows conceptually the same three models considered for the prior, with the substantial difference now that the scale parameter is now C, the true actual values, and the location parameter is 0 here because we are modeling an error, zero mean error, which we have to sum up to C. So we translate the PDF in such a way that this likelihood has mean equal to the C values. And the scale parameters is the uncertainty matrix U. For each model, 10 million vectors were drawn from the joint PDF of the actual and the measured values, from which the consumers and the producers' total global risk were calculated respectively as the fraction of those cases when the all measurement values were within the acceptance interval, at least one actual value, CI, was outside its tolerance interval, and this gives the total consumer's risk, and the fraction of those cases when at least one measured value was outside its acceptance interval, but all the actual value CI were within the tolerance. And so this gives the total producer's risk. These are the results we obtain. We obtain total global risks for the three models when the acceptance region was chosen as coincident with the tolerance region. The plots you can see here are the surfaces of the total global risks versus the acceptance intervals of rhodium content, A2, and the 8 impurities content, A3, where the width of such acceptance intervals vary from the corresponding tolerance interval up to the 3 uncertainty far away. One can see in this example that the risks depend on the acceptance limit chosen for rhodium, A2, but it's practically independent of the acceptance interval of the impurities content, A3. We should say that this kind of plots allow choosing the appropriate acceptance limits which correspond to the suitable risks of the consumers and the producers. So they can be used in such a way to determine the appropriate acceptance region. The second examples, in this case study, we deal with the testing of a specific potassium iodate batch considered as a candidate reference material of potassium iodate purity. These are the tolerance limits for the purity, C1, and for the content of the impurities, C2. Two test methods were used for the determination of the purity of the batch, a direct method and an indirect one. Here there are the corresponding estimates and associated uncertainties. The direct method is based on the SI traceable primary colorimetric titration of oxidants, whereas the indirect method is based on the mass balance approach, where the content of the impurities is measured and then content C1 is directly obtained as 100 minus the other. The prior PDF for the purity C1 is approximated by a univariate truncated normal distribution. The location parameter mu is taken as the mean of the permissible purity interval It is a mean of 99.9 and 100% according to the regulation. The scale parameter sigma is assumed equal to the target measurement uncertainty. Note that in the present study, the scale parameter does not characterize the variability of the conditions of a batch production, as we have done in the previous example, the alloy example, but reflects the variability in the selection of the appropriate raw material for the development of the reference material. So, because of the mass balance constraint, for each value C1 of the purity simulated according to the truncated PDF, the corresponding value C2 of the impurities is deterministically evaluated as 100 minus C1. We consider two possible tasks of evaluation of total specific risks and has two corresponding scenarios for the likelihood modeling. In the first scenario, both contents of purity and impurities are under conformity assessment. Either the purity is measured directly and then the impurities are recovered from the mass balance, or vice versa. In both cases, the likelihood is a univariate truncated normal PDF with location parameter equal to the corresponding actual true value and scale parameter equal to the relevant measurement uncertainty. In scenario 2, instead, both purity and impurities are measured directly and independently. So their likelihood function are modeled by two separate univariate truncated PDF, and then the corresponding simulated values are closed according to the closure operation. Notice that in the case that the measured values are not mandated to satisfy the mass balance, the closure operation can be avoided. Such a situation may occur when the sum of the purity and impurities is smaller than 100% because not all the impurities, for example, have been detected, or when the sum is larger than 100% due to the measurement uncertainty. For scenario 1A and B, we understood that the total specific risks coincide with the particular risks relevant just to the purity. We'll discuss it in a minute. Instead, for scenario 2, we drew 10 million random vectors of the true and the measured values according to the prior and the likelihood function in order to numerically integrate the posterior PDF that is needed for the calculation of the specific risks. These are the particular specific risks for the purity content only. They were calculated according to the standard document JCGM 106. In the present study, the consumer is the regulator defending the interests of the laboratories that will purchase the reference material by the producer. As expected, of course, the consumer's risk to the left decreases for measured values far from the tolerance limit, whereas the producer's risk increases for measured values close to the limit. Let us now move to the total specific risk. We recall that the total consumer's risk of a two-component material is the probability that, although the material was tested as conformant in both its components, it is actually not conforming. This happens when the actual true values of one or both components is out of specification. In this example, however, the purity true value is out of specification when and only when also the impurities content is, because they are perfectly correlated by the mass balance constraint. One of the two is equal to 100 minus the other. Hence, the surface plot on the risk of the risk values versus the two components degenerate into these kind of flat sails, which actually are the three-dimensional representation of the very same curves I've shown just in the previous slide. The collapse of the total risks for two components to the particular risk of one of them is not surprising in the case of compositional data, in which one of the two variables is modeled exactly as the complement of the other to 100%. Let me say that such complementary variable indeed does not convey any further information from a probabilistic point of view. And these are the total specific risks by scenario 2, when, respectively, the closure operation is performed in the likelihood modeling and when it is not. In this second case, hence, we obtained a non-degenerate surface because we were not trying to mandatory model one measure value as 100 minus the other. In general, comparing all the univariate and bivariate scenarios, we have seen that the results we obtained were practically the same, therefore transforming the fact of the bivariate case into a univariate one because of the mass balance constraint. Hence, there is no significant difference between direct and indirect purity test methods if their measurement uncertainties are approximately equal, as it was in the present example. So, to summarize, an adaptation of the multivariate Bayesian framework for conformity assessment to compositional data is under development at the moment within an IUPAC project. The modeling of prior PDF and likelihood function is based on truncated normal PDF, having a covariance matrix that accounts also for the spurious correlations. The mass balance constraint among the quantities can be modeled by Monte Carlo simulations of values that sum up to 100%. And we are working on the application to further case studies such as food objects and gas mixtures. So that's it. Thank you very much for your attention.
Many thanks, Francesca, for your very clear presentation. I saw there was a comment during your presentation saying that J. Cornell should also deserve a mention in the respect of compositional data. I don't know if you took into account also Cornell as a possible source of inspiration in your analysis, but I think that this suggestion could be taken into account.
Well, to be honest, I'm not completely sure that this author was one of the several papers we have been reading about compositional data, but starting from Atkinson, there was a huge literature on compositional data, and I think Cornell is one of the, of course, the representative there. But as we said, we try to adapt the usual, let me say, multivariate Bayesian approach we have developed in the IUPAC CITAC guide to compositional data without resorting to the typical transformation used in the compositional data analysis because of the reason I mentioned. So the fact that the logarithm transformation of the multivariate region and the log transformation of the probability density function involved would have made the context, the framework, very more complicated, also from an application point of view, and also from an easy interpretation point of view. So we departed from the strict application of compositional data analysis.
Thanks. I see that there are two additional comments, so I will read them, and I suggest to have these ones as the last questions to Francesca, as we need to move on. So one is, with the indirect method, what happens if you don't catch all impurities?
Well, I can answer more from a statistical point of view, because I am not a chemist. Maybe Ilya then would, if he wants to add some words. From the statistical points of view of the modeling, finally, all that you are not able to measure expressly, it goes to let me say to the remaining part. You measure something. You are able to measure, for example, you directly measure the content of the purity, and then all the rest is just captured by 100 minus, because in this case we have just two components, but also in the case of more components, all the things that you are not able to measure directly could be encompassed in the closure operation that is 100 minus the sum of the others. Of course, this may have an impact on the uncertainty. You should then somehow evaluate on each of the components. And the fact that you know that you are not capturing everything, I think that could enlarge the uncertainty somehow.
Thanks, Francesca. There was an additional question. Once you have a multivariate model, are you comfortable to decide conformity based on a univariate interpretation?
Well, this is what happens for the second case study I presented, because actually it was a fake bivariate model. It was just a univariate in its substance, because both the prior and the likelihood, because of the very compositional nature between just two quantities, one of the two quantities was always recovered by 100 by the other. So the independent information was just on one variable. This became a proper bivariate problem when we did not force the closing operation in the scenario 2 between the measured values, because we allowed the two measured value to sum up to something smaller or larger than 100%, for example, because of the uncertainty, or because not all the impurities are captured. And so this became actually a bivariate problem, in which from that plots we could say something about the influence of the uncertainty on the risk evaluation. But if we close everything, and if we don't have other source of correlation, actually from a bivariate model, we move to a univariate model in this case. Of course, if you have more than 2, 3, or 4 quantities, and if you have other source of correlation, as in the alloy example, the situation is less degenerate. But the fact that we are using compositional data, you always lose one of the dimensions.
Thank you so much, Francesca. Thanks again for your presentation. The next speaker is Dr. Angelique Bota. She works at NMI SA, the National Metrology Institute of South Africa, and as also the ISRAN co-chair, she will give us a lecture on the development of guidance for the production of high purity reference materials. Please, Angelique.
My apologies, I thought I lost the connection. So thank you again for this opportunity to share with you the guidance that ISRANALYTICA is developing for high purity reference materials. So I'm going to start the presentation just to give you a brief overview of ISRANALYTICA, and then I'm going to focus a little bit more on the new activities of the committee, looking a little bit at the guidance the committee is developing for qualitative reference materials, and then focusing specifically on the guidance for the production of high purity reference materials. And then I'm going to conclude with an exciting announcement. So if we just look at who ISRANALYTICA is, the ISO Committee for Reference Materials. The committee carries out and encourages a broad international effort for the harmonization and promotion of reference materials, their production and their application. REMCO's vision is to be the global center of excellence with respect to issues relating to reference materials. So here you can see the list of all the objectives of the committee, looking at concepts, terms, and definitions related to reference materials, looking at the characteristics of reference materials, how to specify them, especially in view of the required intended use. And then we also support other ISO committees that need guidance on the use of reference materials for their standard development work. And then we also help with the preparation of guidelines. You might be very familiar with ISO Guides 30 to ISO Guide 35 that the committee has developed for reference materials. We also communicate with other international organizations. We have a very strong liaison relationship with quite a range of other international organizations. And then we also advise the ISO Technical Management Board. Then in terms of the stakeholders and the clients of the committee, of course, the standardization bodies, the national metrology institutes that are very involved with the production of reference materials. We also have a whole range of other international and regional liaison partners, as I've already mentioned. The clients, REMCO has a very strong horizontal advisory function. As I say, we advise a lot of other ISO technical committees. Then, of course, the users of reference materials is a very important client, especially the testing laboratories, then producers of reference materials, and then also the accreditation bodies with their responsibility to look at the conformity assessment of reference material producers. If we look at the structure of ISO REMCO, you can see the structure is basically organized to highlight the type of guidance that is developed by the committee. In the center of our activities is the standard that has been developed for the competence of reference material producers, ISO 17034. The standard was developed as a joint working group with ISO CASCO as a conformity assessment standard. And the guidance documents that very strongly support the standard is ISO Guide 35 to establish the characteristics of reference materials, specifically also certified reference materials. ISO Guide 31 looks at reference material documents. ISO Guide 30 looks at the terminology related to reference materials. And then you'll see on the left-hand side of the structure is a whole range of guidance that was developed for specifically the uses of reference materials. And then there's also a few technical reports looking at issues such as qualitative reference materials, traceability, reference material distribution on a global scale. And today I will focus here on the right-hand side of the structure, looking at the new guidance that's being developed for qualitative reference materials, and then also for high purity reference materials, looking specifically into two areas, small organic molecules and also the metals and metalloids. Here I've just listed a few of the other publications that has been published by REMCO. There's very interestingly a note on commutability, because one of the requirements of reference materials is also to be assessed for commutability. And then a very old but very interesting little publication on the role of reference materials in achieving quality in analytical chemistry. Now I can move on to talk a little bit more about the new activities of the committee. Working Group 13 of the committee is developing the guidance for the production of reference materials with one or more qualitative property values. So that guidance document is now being drafted. We're hoping to have a good, strong working draft through the course of this year that we can start balloting on in the committee. So that's quite exciting. This work also started with the technical report looking at reference materials for qualitative property values. In the technical report, you will find some very good examples of reference materials with qualitative property values and how they were produced. And then what I will be focusing on more today is to talk about the work that's been done in Working Group 18, looking at organic purity reference materials, so developing harmonized guidance for the production of high purity reference materials for small organic molecules. So if we look at ISO Guide 86, I can just mention that the work was first started in an ad hoc group of the committee, ad hoc group 4, where we investigated whether there was a need for some harmonized guidance and whether the state of the knowledge has been developed sufficiently to generate this harmonized guidance for organic purity reference materials. This work was also very much informed by the excellent project, IUPAC project on the harmonization of approaches for the characterization of organic purity reference materials. And this is a very important input also to the guidance being developed in REMCO. But of course, in ISO Guide 86, the focus is much more on the reference material production aspects. such as the assessment of the homogeneity, the assessment of the stability of the material, the characterization, and also the establishment of the metrological traceability, and how to develop the statements for the traceability on the reference material documents. So let me just go into a little bit more detail into the major discussion points in ISO Guide 86. One of the first discussion points was whether we need to develop terminology for high purity reference materials and whether we need to work on harmonization of terminology. Of course, terminology is always a very hot topic in the environment of international standardization. So right in the beginning, the working group decided to not really focus on developing terminology, but trying to harmonize on concepts and to develop concepts for high purity reference materials. Another very important aspect of the production of a high purity material is to define the intended use, to communicate the intended use to the customer, because that will assist with clarifying all the other aspects of the production and the characterization process. So the next very important discussion point was the definition of the measurand when you consider a high purity reference material. So the first consideration for the definition of the measurand is what characterization approach are going to be used for the material. And as we know, there are basically two basic approaches for the characterization of a high purity material at this stage. Either you can use an assay approach where you quantify as accurately as possible the high purity component that you are interested in the material. And then the other approach is the mass balance approach, where you assume 100% for the major component of the material, and then you do analysis using orthogonal methods preferably to determine the impurities, and then you subtract from 100%. So when you are doing the characterization of the material, it is very important then to consider the impurities, and some of the discussions in the working group was what to do with substances that cannot be detected and that could possibly be in the material, how to quantify, how to determine the limit of detection, how to define these impurities, and then also very important whether it will be required to include these impurities in the measurement uncertainty statement, and how you would actually include it in the measurement uncertainty statement. So these have been some very involved discussions in the working group. Then another aspect that's very important for the definition of the measurand is the structure, especially when we're talking about organic molecules. So you can, of course, consider the three-dimensional structure for the smaller organic molecules, where you need to consider different isomers. And then also, as the molecule becomes bigger, you might need to consider the even four-dimensional or the activity of the molecule as the parts of the molecule start folding onto each other. So this is also a very important discussion that is happening in Working Group 18. Then, considering the characterization approach and what to do with the structure or the impurities in the material, it is also important to consider whether the material is going to be characterized to be independent of the methods of measurement used, either by the producer of the material, or even also considering the users of the material, or whether it will be required to define the measurand as an operationally defined measurand. So this is also being debated and discussed, how to approach these distinctions in the working group. And then considering again the intended use of the material and what information to provide in terms of the intended use of the material, you also need to consider this for the definition of the measurand, how the measurand will be defined for the customer, how the customer will be able to use the material depending on the definition of the measurand. Then after the definition of the measurand, the next aspect to consider is the metrological traceability. And of course, when we're talking about metrological traceability, the first consideration is how to establish metrological traceability also for your high purity materials. Basically, in ISO Guide 35, the two most important approaches for the characterization strategies that can be used to establish metrological traceability is to use a single method in a single laboratory. That is one very important approach that is also often used by the National Metrology Institutes. And then a more widely used approach is that of a collaborative study, where the material is distributed to a network of laboratories, competent laboratories, to characterize the material, and then the statistical analysis of the data is used for the value assignment. In ISO Guide 35, these strategies are elaborated some more. Of course, you can see there the important one of a single method in a single laboratory, but another variant of this approach that is used very often is using a single method in a single laboratory with comparison with a similar CRM. So this is basically where you will have a primary certified reference material, and you will use this primary certified reference material to value assign secondary reference materials. And then there's collaborative studies, and then a specific application of a collaborative study is where you are using a collaborative study of a network of competent laboratories for an operationally defined measurand. And then you can also consider formulation methods where techniques such as gravimetry is used to add components to make up a synthetic reference material. Apart from the establishment of the metrological traceability for producers of reference materials, it's also very important to consider what to put on the reference material certificate as your statement of metrological traceability. So just to start off these discussions and to stimulate the thoughts a bit, I've went to look at a few reference materials certificates and what information is provided in the statements of the metrological traceability. So here you can see a certificate for a solution of dibutyl phthalate acid ester in methanol. And in this statement, you can see it is basically the material was manufactured using a high purity material, but there's no information provided about the purity assessment of this high purity material. So this will be quite important information for the user of the reference material to have some more information about how the purity of this high purity material was actually assessed. It also almost looks like this material is defined as a operationally defined measurand, because the only real method that is used here is the GCFID method. In the next certificate for an Aldrin standard, you can see there's quite a lot more information about the purity of material. There's quite a range of techniques used. However, maybe the techniques is not orthogonal enough to give you a comprehensive view of the purity assessment of the material. Maybe some more work could have been done on this. And then also, when you look at the manufacturing notes on this material, you can see it basically only refers to the gravimetric preparation. So looking at the calibration of physical measurement standards such as mass and volume. Then the third certificate, another certificate for Aldrin. Here you can see very nicely that the metrological traceability is stated to be to a certified reference material, the NIST PS1 benzoic acid standard for quantitative NMR analysis, and then there's quite a lot more information about the certification process that was used for this material, where high resolution quantitative NMR measurements were used. I didn't provide all the information here, but here you can see a bit more clear picture about the metrological traceability of this standard. So just in conclusion, talking a little bit about what to expect or what would be a good amount of information to find in the statement on metrological traceability and a reference material certificate. It might be difficult to put all this information in the statement, but usually the certified reference materials will be accompanied by a certification report that could have some more information. So the statement could be quite short and to the point with some more additional information in the certification report. But here you can see the important things. Very important, and number one, a complete description of the measurand, a correct expression of the quantity value and uncertainty. So this refers to the measurement scale that was used for the assigned value. Very importantly, the characterization strategy, whether it's a single method or a collaborative study, what measurement principle was used, the measurement model, then also the information on the measurement standards used for calibration, the sources of conversion factors and correction values that were used in the measurement model, some details on the method validation that was done, especially with respect to the measurement trueness evaluation, details of suitable quality control measures, a detailed uncertainty evaluation, and then other evidence that could be useful is something like a comparison to other traceable certified reference materials. And then I just want to mention that we also have a new working group that is led by Zoltan on looking at purity reference materials for inorganic materials. So there is an approved work item for ISO Guide 87 to produce harmonized guidance for the production of high purity reference materials for metals and metalloids. This group is still very young. The work is just starting. So if there's anybody on the webinar today that's interested in this work, please contact Zoltan, and Zoltan will direct you to your national standards body to be registered to become part of this working group working on this new guidance. So in conclusion, I mentioned that I have a very exciting and very important announcement, and that is that the ISO Technical Management Board has just made a decision to establish a new technical committee for reference materials, ISO TC 334. So ISO REMCO will now be transformed into this ISO Technical Committee. So this is very exciting news, because for the first time in 50 years, ISO REMCO will now be able to produce international standards. So the first order of business will be to review the guidance that the committee has developed over the years to see how it can be transformed into international standards. And we're hoping that this will promote the guidance even further and allow for the use of these standards also in regulatory processes and regulations. So this is quite exciting for ISO REMCO and for promoting the work of ISO REMCO and for providing you with some even better guidance on the production and use of reference materials. With that, I want to thank you for your attention, and I want to thank you, ISO REMCO, for all the hard work over the years. And then I'm also open for questions. And if you need some more information about the committee, you're very welcome to contact us via the website or by email. Thank you very much.
Hello.
Thank you so much, Angelique.
I have a question.
Yeah, sorry.
Is it? I send by the chat a question.
Yes, I was going to read it after.
So okay, thank you.
Thanking Angelique and congratulating for the very important news, because yes, everyone had difficulties in using the guidelines from ISO REMCO because they were not ISO casco and so not international standards. And it's very good that now this new technical committee will be for sure of a great help to everyone who has to deal with reference materials and needs to have standards to work with. And yeah, I saw that there are some comments on the chat. The first one was a comment related to the fact that the measurement uncertainty associated with a given property value of a material is related with the quantity value, not to any impurity present in the material. Angelica, would you like to comment on this?
Yes, definitely. This is true. The concern that the committee has, and that's why we are considering impurities, is just how the material will be used, because of course the certified property value will be the assigned value of the high purity component, the main component of the high purity reference materials. But if there are a considerable amount of impurities in the material that are very similar, especially to the main component or the component for which the property value is certified, then you could have some issues with interferences depending on how this material is used. So that is basically the reason for the consideration of, do we need to quantify or assign values also to the impurities in the material? To what extent do we need to qualify the intended use of the material for the users? And what information is needed in terms of the impurities in the material for the users to make sure that they don't have problems when they're using the material in certain applications.
Thank you, Angelique. So the comment of our colleague from ISRAC was that asking to give advice on what is recommended that a laboratory has to do in case there is no traceability for specific standards. There is a practical example. For example, a laboratory that analyzes traces of veterinary drugs when the drug is not commercially available with traceability to ISO 17034. Is it possible to have advice in your guidance documents on how to deal with these situations?
Good afternoon, everybody. It's 2 a.m. in Sydney as you listen to me, so my apologies for pre-recording my contribution. But I trust you're all well, and while we do not meet in person, hopefully we can benefit from a wider audience on Zoom. I thank Ilya for inviting me to speak. Although I'm very much the junior partner of the project on conformity assessment that you're hearing about, I value greatly what I've learned from the group. The strength of the work we do is its practical nature. Cutting-edge theory is applied to a number of real problems, from environmental assessment to the quality of sausages, and perhaps to the work in the courts. If I may now just go to my slides. I think I'm sharing that with you now. I think Ilya has made a wise decision to ask me to talk about something I actually know about, giving expert opinion in court. My work with IUPAC has been mentioned in court judgments, and I play on my association with the union to give my evidence kind of extra gravitas and seriousness. And in my talk today, I shall discuss the use of Bayes' theorem in expert evidence and how conformity assessment could contribute to the court's understanding of scientific evidence. So, scientific evidence, or expert opinion as we call it, in a court or tribunal is allowed if it's given by a person who possesses specialized knowledge based on the person's training, study, or experience, provided that the opinion expressed in the evidence is wholly or substantially based on that knowledge. But experts cannot usurp the function of the so-called trier of fact, i.e. the jury, or a judge acting without a jury. And an expert is not supposed to look at any other evidence outside their expertise. So they shouldn't play the amateur detective so much beloved by TV series. Often a highly intelligent academic expert comes to court with the idea that he or she will apply their intellect to all aspects of the case, arguing they can interpret their evidence much better if informed by a knowledge of the background and the other facts. No, 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 says the court. Thank you very much for the offer, but this is not your job. So there is a line that we cross, as it were, at our peril. In addition, courts are very suspicious about statistics. We see some very famous quotes from Mark Twain, even Winston Churchill. I like the "I only trust the statistics I make up myself." And the last quote on the slide tells us, is from a case that became very famous in England a few years ago. And as you can see, the court there definitely didn't want to hear about statistics. So that brings me to Bayes' theorem. Here's Thomas Bayes. There's me in London in front of his tomb in Bunhill Fields. And of course, we all know that it was Laplace who probably, or did in fact, say the Bayes' theorem as we know it today. So what does Bayes' theorem in a court of law look like? Well, like Bayes' theorem anywhere. The posterior probability of guilt of an accused, given the evidence, is proportional to the likelihood times the prior probability of guilt. Now, of course, we have to think about what all of that means, and indeed, what is the probability of finding the evidence given the guilt, the likelihood, and then how do we bring it together? Unfortunately, courts don't like statistics, and they certainly don't like Bayes' theorem. Even though it's at the heart of giving DNA evidence these days, there is a problem. And in fact, there are many problems, and I haven't got time to go into them. But essentially, if a witness gives a probability of guilt of the defendant, what's left for the court or the jury? We just need to establish the threshold probability, and that court can go home and leave the whole thing to experts and perhaps an AI robot. And so what does probability mean in a court? Here are some suggestions that I've made in terms of the different kinds of trial that we find. So a criminal trial, we all know that the guilt has to be proved beyond reasonable doubt, and courts are very careful not to put a probability on it. I've said 99% plus just to keep the debate going. At the other end, in civil matters where one large corporation sues another, the test is on the balance of probabilities. One side's got to win, one side's got to lose, but there's no point, there's no reason why one should get any special treatment. So 51% plays 49. And then in the middle, and I put this in because it's actually what I do a lot of in tribunals, so sports drugs, as we shall hear, there's something called the Brigginshaw standard, which is to the comfortable satisfaction of the court. Again, nobody's ever put a percentage on it. I'm offering 75%, whatever that means. But we could set limits for these probabilities of guilt, and we could apply conformity assessment to the decision of guilty or not guilty. Think about a guilty verdict as the equivalent of crossing an upper acceptance limit for innocence. Of course, the evidence is highly correlated, it's just what we do. And for cases that rest on scientific evidence that can be quantified, then we should be able to apply our knowledge to the problem. So let me start with a fairly clear example, that of doping in sport. I give opinion about the analysis of substances in human and animal athletes. I appear for prosecutions and defence, and although I participated in a very big Australian case a year or so back in which a whole team of Australian rules footballers was disqualified for a year for taking a banned peptide, I do most of my work with racehorses. And so here is something from the Sydney Morning Herald, which is the main newspaper in Sydney. I managed to get onto the back page for saying that a cobalt level in a horse's urine was off the scale. This was because my spreadsheet, I hadn't made the cells wide enough, and so there were hashes, and I was invited to explain, and I was going to tell them about spreadsheets, but in the end I said, oh no, Your Honour, it's just off the scale. And there was a man from the paper there, so I got into the newspapers. Okay, so in horse racing, a horse isn't allowed to race with more than 100 nanograms per mil of cobalt in any form in its urine, and this is a standard more or less across the world. I helped to underpin the limit when it was first introduced into Australia at 200 nanograms per mil, as it happens, by establishing the distribution of cobalt in racehorse urine, and thereby allowing calculation of the probability of a typical horse presenting with urine over any particular mass concentration. So here's one of my reports. As you can see, the amount of cobalt in racehorses follows a very nice log normal distribution, and by deciding where the judicial limit might be, we can give probabilities for finding that level, that mass concentration in an ordinary horse. The interesting problem here of statistics was that I had no ground truth to work on. I was just given data from racing horses. So of course we don't know which ones had been administered and which hadn't. The argument is if the majority of them follow a distribution and there's a few outliers, those outliers perhaps are the ones that were administered in some illegal way. But the question is, how do you establish that when you've only got the data? Well, no time to go into it, but eventually it was accepted in court after quite a long appeal with other statisticians and so on. We won, and this is the kind of result that's happened. So you might ask, what would be a guard band for given the measurement uncertainty of the mass concentration of cobalt? The ISO 17025 accredited laboratories in Australia claim a relative expanded uncertainty of round about 10 to 20%, or 10 or 20% at the 100 nanogram per mil threshold, saying in their certificates of analysis that the range contains the true value with a probability greater than 99.7%. They've taken 3 standard uncertainties, rounded up to 1 significant figures. I've got problems with this and would like to see a proper uncertainty budget, but that's another story. So is there a guard band? We have a result, we have a measurement uncertainty. No, we don't. The level of 100 nanogram per mil is based on measured data and is arbitrary anyway. So the argument is that any allowance for uncertainty is already made in the setting of that level. However, no prosecution has been started for a cobalt concentration of 101 nanograms per mil. And both the A and B samples usually are pretty comfortably over the limit. Unfortunately, the authorities have never commissioned a proper statistical analysis that could inform a guard band. I mean, I'd be very happy to do one. So it turns out that for each prosecution, experts can be called to argue over the particular results reported. It keeps me in work, actually, of 1 or 2 of these cases a year. I presume that there would be an unwritten principle that if there were a guard band, it would favour false negatives, i.e. that not guilty when you're actually guilty, to avoid the false positive, taking an innocent trainer and arguing that they're guilty. I'm not sure what this is in terms of consumers and producers. You can kind of work it out yourself. Let me now turn to a murder that I did last year. I should say a murder case I was involved with last year. This was a cold case, murder committed in 1997, revived 20 years later and came to trial in 2020. The aspect of the case which I gave in evidence was in relation to lead isotope fractions found in bullets in the body versus bullets seized by the police from a box of bullets in possession of one of the defendants. I should say that the gun was never found. There was no direct evidence linking the accused with the murder, but they did know each other. They were business partners. There were two issues I was asked about in relation to the evidence. First, the university laboratory that did the analysis by inductively coupled plasma multi-collector magnetic sector mass spectrometry, which I hadn't come across, but is incredibly precise. They were specialized in geochemical research. They hadn't done forensic stuff before. They were not accredited for their measurements. Appeared they'd never heard of measurement uncertainty, method validation, or anything like that. The professor who gave evidence said he trusted his judgment, that his results were absolutely correct. They used a NIST standard, good, but they used it to establish repeatability, not trueness. And the repeatability is of the order of about 0.01% relative, which, you know, as I said, is pretty good. But they offered results as graphs of ratios that didn't actually cover all compositions. There are 4 lead isotopes, 204, 206, 207, 208. So you need at least 3 independent quantities to uniquely locate a sample. Okay, the fractions add up to 1, and of course this would be ideal for the kind of thing, conformity assessment problems that we're looking at in our little group. I don't think it's going to happen. So here's some data I worked on. I've made anonymous, so I'm not going to tell you what the different dots are, other than to say they're bullets. I created the error bars according to the way I did it, but you can see that there is overlap between the different kinds of dots, and this perhaps shows that there's some linkage in the isotopic content between the bullets. This was the kind of graph that was shown in court, and as I point out, we see 208 to 204, 207 to 204, but in fact we don't have, it's a 2-dimensional graph, and actually that doesn't uniquely define the composition, and they ignore that because 204 is very small, nobody cares about it. However, I was very keen to press the lack of validation of the technique, as you can imagine, but in fact nobody wanted to hear that. Because the case eventually revolved around the interpretation of the match. So the question was, even if the lead isotopes of the contents of the bullets did match between the body and the box, what does this tell us about the guilt of the accused? The professor of geology in his statement actually said, quotes, "The evidence implicates the name of the defendant as being involved with the murder of Carlyle." Well, this violates the principle I was talking about earlier, but it's also a wrong statement statistically. And you might like to think about what's the problem. Interestingly, although I was going on about method validation, of course, if this statement can be attacked, even if the results were okay and there is a match, what does this say about the guilt? And at that point, the lawyers just gave up, because if they could prove this point, they don't need to argue about validation. So let me return to courts and Bayesian statistics. Although still in dispute, courts are more comfortable with likelihood ratios. They see that as a kind of halfway probability house, if you like. So in words, the likelihood ratio is the probability of finding the evidence, given the truth of the prosecution hypothesis, i.e. the bullets in the body came from the defendant's box of bullets, that's the prosecution hypothesis, divided by the probability of finding the evidence if the defense hypothesis is true, i.e. the bullets in the body came from a different box of bullets. Well, likelihood ratios are often presented to courts either as the ratio themselves or as words. There's a big debate in sociology, kind of theory of psychological theory, I should say, in this area, that juries don't like numbers, aren't very good with numbers. And so we ought to say things like very strong support or weak support, and they'll be much more comfortable with that kind of thing. And you can see that the likelihood ratio, probability of finding the evidence if they're guilty over the probability of evidence if they're not, if it's bigger than 1, the prosecution hypothesis is supported. If it's less than 1, the defense hypothesis is supported. Usually we're talking about the bigger than 1 because it doesn't get to court if it's not. And if you think about it, DNA evidence, which does this all the time, the match of DNA of a suspect and DNA found at a crime scene means the top line, probability of the evidence if they're guilty, is 1, essentially. And what's the bottom line? Well, turns out there's about 1 in a billion people that have that can randomly be expected to have the same 10 markers that are used in DNA evidence. So the likelihood ratio is 1 divided by 1 over a billion, i.e. a billion, and the prosecution's hypothesis is extremely strong. And we're all very happy with that. We accept DNA evidence, all good. So what's the likelihood ratio for our bullets? I hope you've had a chance to have a think about it. So to answer the question, of course, we need to know how many bullets were made from the same pig of lead. That's apparently what they call it. So you melt a lot of lead, may come from ore bodies, may come from scrap lead, doesn't matter. Once it's melted, we assume it's got a homogeneous isotope fraction, and we pour it out and we make a heap of bullets with it. So the question we need to know, how many bullets came from that pig of lead and how many of them came to Australia in 1997 and could have been purchased by the murderer? Well, as it happens, we don't know. This information is just not available. In the end, they could not even prove that the manufacturer to go and ask them, although there was a suspect manufacturer, and we did ask, but their records were long gone, and they couldn't tell us at all. And more to the point, the prosecution and the professor of geology who did the analysis never contemplated this question at all. They saw the match, they said they were guilty. Well, let me look. So say there were 6 boxes of bullets. I don't know they were, but let's say they were. Here's a picture of bullets on a gun shop shelf. So only that box in possession of the defendant supports the prosecution case. So we're assuming they've all got the same bullets, kind of bullets with the same isotope fractions in them. We assume that they would all match with the bullets in the body. So there's only 1 out of those 6 that supports the prosecution hypothesis, the one that was found in the defendant. The other 5, wherever they are potentially owned by the murderer, and the likelihood ratio finishes up as 1 over 6 for the prosecution, 5 over 6 for the defense, 0.2, i.e. extremely weak support. In fact, no support at all. The evidence supports the defense rather than the prosecution. And you can generalize that. Obviously, if you've got n boxes, it's 1 over n minus 1 over n, and so on. So really no support at all for that. Now, the arguments about the admissibility of the evidence were heard in the Queensland Supreme Court, and the judgment struck out all references to bullets and their analysis. My written evidence was accepted without need for cross-examination, and you've seen at the subsequent trial the accused were acquitted. In my view, the professor of geology had made the mistake of becoming too involved in the case and strayed way out of his expertise, which in the end, as the late Paul de Bievre used to say, not fit for the purpose for the intended use. It's unfortunate because I've tried to contact him and suggest that he help in a project doing some of the things I've suggested earlier, but he has not returned my emails. The only evidence really in the trial was the box of bullets of the defendant, and so this evidence being ruled out actually meant the case still went ahead, but a judge found the defendants not guilty. And of course, in the British, American, Australian kind of system, the onus is on the prosecution to prove their case, not the defense to prove theirs. So the defense didn't have to find any other boxes of bullets. It just had to suggest that there was a possibility, and the prosecution hadn't taken that into account. So in conclusion, let me say, courts would rather not rely on statistics, even though they're always making conclusions with incomplete information. In terms of judging the weight of evidence, likelihood ratios are used, but in fact, they're often misinterpreted. And considering the probability of guilt from a conformance standpoint should be considered, because I think we might be able to help the courts get their head around this idea of how we can accept in a probabilistic way the evidence. And that's the end of my story. So thank you very much for listening. I hope the rest of the webinar goes well. I look forward to seeing the videos, and I hope you've enjoyed yourself. Thank you and good afternoon.
Wow, great, as usual. It's a pity that Bernd was not with us, because I'm sure that there would have been a lot of questions for him. But well, next time, I hope next time. So I saw that there were many people asking in the chat on where to have links for the event. And in the invitation prepared by Ilya and forwarded to all of you, there were the web pages of IUPAC and CITAC, where you can find the links of the lectures. I wrote it down in the chat, so if you want, have a look at it and take notes of it. As for me, thanks to everyone, and I would like to pass back the microphone to Ilya for the final remarks.
I would like to thank our host again, Zoltan, and moderator, Michela, and every speaker. And thank you also those who was with us, participants. Now it is 129, but in the middle of the webinar it was 178. I understand that the time is different in different countries and continents, and so it is not surprising. Anyway, it's honor that so large number of colleagues was interested in our work. Thank you again, and see you in Jerusalem or in Tel Aviv next year in January. At the workshop, I mean, it's the continuation of our workshop. Thank you.